morning. Welcome to the CIDCI Online Salon Series. CIDCI's mission is to accelerate innovation, disruption, and change to improve the built environment. We create networks that share knowledge, experience, and ideas through productive dialogue. CIDCI is a not-for-profit organization that relies on your financial support to provide these programs. Thank you to our sponsors who make all of this possible. CIDCI is proud to announce the start of our Innovation Lab earlier this month. Led by UC Berkeley's Sarah Beckman and Rachel Zombach, this online program uses a self-paced format to create a community of practice within the AEC community. The 6-module program will teach participants the mindsets and skill sets associated with the innovation process. The content for the modules will all be delivered asynchronously via Google Classroom and includes videos, readings, and discussion questions. Participants can access the material at any time during the 2021 session. Details are available at the CIDCI website. CIDCI is also planning to start our fall forum announcements. We've entitled this session, Inspiring Innovation in a Re-Emerging World, and will begin October 4th and run through October 8th. Over 5 days, we'll spend our mornings or evenings, depending upon your time zone, exploring a wide range of issues, including how building owners view our return to work post-pandemic, what failure can teach us about resiliency, and examine some startups changing the world. All events will be online. If you see something you want to share with a client or friend, feel free to direct them to the CIDCI website to hear recordings of all of our events. Okay, here's a bit of information about how today's session will work. We're recording this presentation and we'll place it on the CIDCI website as soon as possible. If you have questions or comments during the presentation, please use the chat box. Today's session will run for 60 minutes. Today, we will explore DfMA, Design for Manufacturing and Assembly. The DfMA methodology, with its foundation of technological innovation, is transforming traditional construction processes. 2 case studies will describe how it adds value to those involved in all steps of the construction process. Our speaker today is Dr. Peter Court. He's an MEP delivery leader with an engineering doctorate in lean construction. With over 40 years in the construction industry, Peter has delivered a wide variety of projects across various sectors in the UK, Canada, and Australia. He's a passionate guy, as you'll see, and is particularly interested in driving efficiency in cost, labor, productivity, and most importantly, improving current health and safety performance, thus transforming the way we all construct. Peter, we're so delighted to have you join us this evening from Great Britain.
Thank you, Margie. Can you hear me okay?
Yes, you sound great.
I'm not muted, is a good start. Okay, so hello everybody, and thank you very much for allowing me to speak today. It's a real pleasure and it's a real honor. So a little bit about myself first. So Peter Court, I've been an MEP project delivery person all of my working life, most of my working life. Latterly moved into consulting, particularly in lean construction over the past 3 years, and really just try and implement my thoughts and experience, I guess, directly into the industry. And I've had remits in Canada, west coast of the USA recently, UK and Ireland. So the agenda for today is the route to where I am. And it's really my story that's spanned the last 20 years, and I'll explain that briefly. The objectives of DfMA and the expected outcomes and methodology, 2 case studies, as Margie said, and a little bit about the next generation of DfMA, which really focuses on the value-added side and reducing the cost of DfMA. From an MEP perspective, and then a short amount on benefits assessment, and then if there's any questions. So I'm going to whiz through this fairly quickly. So I started life as a project engineer in ventilation, and where we used to do our own drafting and engineering and commissioning. And as you become better at that, you then get promoted. So that happened to me. I became an operations manager in a large ventilation company, ABB Flat. And that led me to believe, by becoming an operations manager, that I'd hit my level of incompetence, I call it, so the Peter Principle. So I had a realization of that at that time. So being a self-developer, I undertook a diploma in management studies, because I thought, well, I'm an operations manager and I need to learn how to manage people, not just projects. So that made me a slightly better manager. And then larger projects came along, and that meant managing different people on more risky and complex projects. That led me to another Peter Principle moment, because as I'll describe perhaps a little bit on the next slide, a construction business is the sum of all of its projects. So each project is a business in its own right. So a large project has an impact on a construction business, or in my case, an MEP business, and it can really dictate the outcomes. And that also flows into customer satisfaction, because if projects can go wrong, then it displeases everybody. So I undertook an MBA on the basis that I can either become a better line manager or manage larger projects, which requires a different skill set. So then big projects became larger and more complex, and I'll touch on some of those shortly. And during the implementation of one of my projects, I met Dan Jones, as a co-author of one of the world's leading lean books, based on their research into Toyota. And that gave me yet another Peter Principle, because I learned about lean, I learned how to see. So I undertook this engineering doctorate that Margie talked about, and that was to bring lean thinking into construction as a practitioner, not just as a pure researcher. And I guess I could classify myself as a production systems implementer in construction. So to touch on project characteristics, so through the course of my career, I guess I started in the bottom left corner, where projects are low complexity and low value. And then they move into still a low value, but higher complexity, and then perhaps a higher value and lower complexity. And these are characteristics of the projects I've worked on. And then right up into high value and high complexity. So the characteristics of the person managing those projects needs to change, because needs to develop, sorry. In the bottom left-hand corner, you virtually do everything yourself. In the top right-hand corner, you need to be a completely different person. You probably need to be a diplomat, a negotiator, a HR person. You don't necessarily need to understand the technology of the project that you're implementing, because you have people that do that. So you need to understand how to manage complex interactions between people, and more complex project value chains. So I'm just going to tell a few stories about my projects. So the first major projects I undertook about 1990 was the channel tunnel ventilation, and this was 4 main fan stations in the UK and France. And the system comprised running tunnel smoke ventilation and service tunnel pressurization. So big, heavy engineering projects. So it's still MEP, but a different scale of MEP. But in essence, it's a railway, which led to my working with ABB in the UK, my next project. So in the privatization of the railway in the UK, signalling upgrades had to be undertaken to keep up with more modern signalling methods, and to get more out of the existing infrastructure in terms of railway routes. So this was a major scheme between London and Surbiton and Woking, which is going into London. And the reason I was asked to do that is because it's a railway. So the CEO of ABB in the UK said, Pete's been on Channel Tunnel, that's a railway, he can do this. So this was implementing a complex mechanical and electrical system on a live railway. So my big key learning on that was, it was all about complexity of the project, managing people that are experts in railway resignaling and trackside civil engineering and logistics, and getting the right person to the right place at the right time. So that was a real challenge, and it spanned 2 or 3 years, and it was a very difficult project. So from there, ABB moved me on to another project, which was a hospital. So not having done a hospital before, but by then I was very aware, or more aware, of complexity and things that support project delivery, and especially logistics. And ABB at the time had, they owned railway manufacturing, or rail carriage manufacturing facilities. So they had some lean people. So I engaged with one of those, and we actually called it trying to implement best practice. And that best practice was really taking on learning from MEP productivity research that was in the public domain at that time in the UK, from an organisation called BISRIA, which is the Building Services Research Institute or Association. And they had a series of recommendations that we were stressing, trying to implement, as well as building on your own experience and building that into the project delivery systems. And this is a PFI project, which means it's on tight time scales. You have to finish on time. There's severe penalties if you don't. And it's a large and complex hospital project. Everything you would expect from an MEP delivery within that. So during that, this was a Bovis Lend-Lease job, as they were called then. Dan Jones was working with Bovis in London. So Dan Jones came to see us. And I learned all about lean just by spending a day with Dan, and that put me in touch with the lean world. And via Google, I learned about the Lean Construction Institute, and that's how I attached myself to them. So I learned to see, I started to learn about waste, and also read his book. So that gave me an appetite of one of these Dr. Peter principle moments that I actually don't know enough, so I need to learn more to make myself more capable to understand how to implement these fantastic methodologies from manufacturing into construction. And if you think about assembly, obviously the product, the car or the lorry or the aeroplane, is designed very well. Everything is designed to fit together perfectly in the best possible way, using the right equipment with trained people, obviously work cells. There's a lot more to that, but think about that and compare that to construction, how we generally undertake construction work. So in learning to see, this is what I saw. So just walking around the various projects that we were involved with, I took pictures, and I've taken thousands of pictures, and these were from 2004, something like that. So generally quite poor. So you can see from these pictures that process waste is prolific. Sites are generally congested. Workers improvised. They're never weren't provided with the appropriate equipment. Workers were generally fitted to the work in unergonomic ways. Trade stacking, out of sequence working. The work was unbalanced in terms of the time allocation between various trades. Damage was rife, leading to snagging. Quality was generally poor. And that didn't stop there, because I've taken recent pictures just walking around different sites, and these, it's the same sort of thing to a greater or lesser degree. Some sites are tidy. But as you can see in that middle picture, that's, I think it says Bazzy's workbench. So he's made that himself got some casters and a pallet and knocking some wood together. And that's his workplace, because we don't provide generally the right equipment for our operatives. So an output of my research is a production system I developed. And just to explain the stages of this, from the site perspective, it's about balancing work with tact planning. And what that means is equalizing the amount of work done in a construction zone in an amount of time with that particular team. So in this case, it's a week beat, we called it. And I got the concept of that from period flow control, which is referenced in a document I'll come on to next. Quite an interesting read. And I think it was how Spitfires were built in the Second World War. And this is about feeding the right amount of equipment at the right time to each team, and the team cycles on to the next zone on the next week, and the next team comes behind him. So this could be the module guy fitting modules. The next guy could be fitting branches off modules, or ductwork, or dry lining, etc. It's about balancing the work. And each of these teams are provided with trade-specific designed ergonomic workplaces and the right tools, everything for the person, for the parts, for accessibility, and methodologies to receive and replace materials. Sorry, a bit delicate there. So the logistics function is fed with parts using ABC parts categorization. And this is a manufacturing technique which looks at categorizing parts on a Pareto basis. So the fewest parts are the most expensive. So in a car, it will be an engine, a dashboard, etc. That's type A. Type C are the thousands and thousands of small parts, nuts, bolts, washers, clips, etc. And B parts are everything in between. And obviously, you need all of these to make a complete system without having to go back and finish bits and pieces. These subdivide themselves into made to order and made to stock. I won't talk about that now. They're described in documents I'll refer to, but it's important from a scheduling point of view, because if you are going to lead into a DfMA environment, made to order materials have a lead time, and instead of those going direct to site in a traditional way, like pipes, bolts, etc., they have to go to a pre-assembly facility with equipment such as pumps, other equipment, heat exchangers, calorifiers, whatever they are, to be incorporated into modules which themselves have a lead time. So it's important to know those lead times, because you're procuring for DfMA, and even a step before that, if you're undertaking modeling, you want to model with your specific items. So you select your equipment to suit the modeling process, to then be manufactured, to then be delivered on site, to site in the field just in time. So it changes the project value chain somewhat. So this postponement function can be in the supply chain. It can be a facility in its own right if the project is large enough. And then these components are parts kitted direct to the point of use to be incorporated with modules to form complete systems. And that applies to a concrete structural frame if it's precast. You want everything you need to start and finish the job in that allocation, in that zone. And the agility dimension is because no two zones, if you're building a hospital, for instance, no two zones are the same. So you want to be able to, either on a Kanban basis or the way you assemble modules, which I'll come on to in a while, that gives you that agility, because not everything's the same. It's called mass customization in the way I can describe it later. So I could honestly talk about that forever, but I can't, because I've got 45 minutes. So it's all in this, my thesis, and it's in plain English. So, you know, please feel free to just download on that title and you can get the whole thing. So North Staffordshire Hospital was my laboratory to implement the construction system. And it's not a very clear picture, but you'll see the new build area here. And it was on an existing hospital. So it was built alongside an operational hospital. And so there was a phase here, which is maternity oncology, hub and wards here, hub, ward fingers, and the diagnostic building here, accident and emergency, and the CSSD, the sterile unit, with a large plant room underneath and a big boiler room over here, car parks, etc. So yes, my director at the time, he was my industrial sponsor for my engineering doctorate, and his instructions to me were, don't screw it up, because there's a lot at stake. The MEP element of this job is about £100 million. The labour content, especially if you're self-delivering and you include the labour content of specialist subcontractors, is about 23 to 25% of the value of the project. So that's £25 million on a £100 million project. If you slip 10% productivity on that, that's £2.5 million. That's 2.5% of your project value, which is your net margin. So labour is the biggest variable. Thinking about projects being a business in their own right, they can affect the financial outcome of projects. So it's very important to control that. And this is a case study I'll talk about in shortly. So the next project I implemented the production system, sorry, is the Northern Water Treatment Plant in Queensland. So you can see it there, and it's in rural Queensland. It's a case study I'll talk about in a moment, but my role on that was to DfMA the whole project from an MEP perspective, and various concrete components such as the calorifier tanks and the unitized cladding systems and so on. So Montreal, this is another case study I'm not going to talk about today, but that is the thermal plant room, which is a very complex installation and was on top of the last building to be formed. And this contains all the prime movers, boilers, steam generators, etc. you need to commission the hospital. So it's in the wrong place, being on the top, because it's the last thing that you build, but the first thing you need for commissioning. So that was a challenge. I'm not going to talk about that today, but it's a case study if anyone's interested. So the aims and objectives of DfMA then is to transform traditional construction processes into a modern process of assembly, really, with technological innovation. Using DfMA, which is on-site assembly of modules and kits of parts to form complete systems, in the way that manufacturing does this. If you watch A380 Airbuses being built, every step is thought through, every component fits together perfectly in a takt time. With ergonomic workplace design, so the work is designed to fit the worker within a synchronized production system, resulting in fewer on-site operatives carrying out safer, more productive and simpler assembly tasks for a shorter period of time, and really adding value each step of the project. So in a lean system, the customer is the next step in the process. So obviously the completed facility, the user or the owner or the occupier of that facility is the customer of the previous step, which is commissioning. And commissioning is the customer of the install. And generally installation overruns, commissioning gets squeezed. And then that delivers a poorly commissioned building. Not always, but there's lots of research papers say that it does happen frequently. So in terms of implementing this on projects, so the biggest message here is that you have to create this, whatever you think this is, but whether it's a production system into creating projects or it's just DfMA, you have to create it. And lessons I've learned when you're too far down the design funnel is that it's too late. You have minimum impact. And this design funnel basically represents the start of a design process where you may want to iterate your design. And obviously you want to do that, choosing by advantages, etc., etc. And then as you move down the funnel, you're increasing definition of what you're designing, you're integrating things, and then things start to get locked down. So this can be LOD 400, for instance. This can be LOD 250. The two different funnels are if you've got your own, let's call it a module family, a component set, then your choices or your funnel is narrow because you've made some decisions already on how you're going to do things. And obviously it's wider if you don't have that. So there's really a benefit of strategic and technical solutions. But really the success starts here by creating the environment that feeds this process. And I'll just put some general headings there. Is understanding the customer's requirements. So the customer might not be interested in DfMA, especially if it's got a premium cost, which in some cases it can. Core values of the business. So an example of one of those of the previous company I've worked for, Langer Rourke, that every worker has the right to go home safely after a productive day's work. So don't put him in a position where he can't achieve that. especially from an ergonomic point of view. So you might have overarching aims and objectives of the project. It might be to save 30% of time, to have 70% pre-assembled off-site, to have much less labour on site because you can't get skilled labour in short supply. Certainly in the UK, I understand in the US also. Creating DfMA guiding principles, which means how the people in the stakeholders need to work to make this happen. Ground rules, sorry, design parameters, how modules need to be designed, or how structural pre-assembly needs to be designed, how things interact and connect with each other. Difference in tolerancing, because you want things to fit first time without modification. And when they're in, they're accessible, maintainable, dismantleable, all the ables, if you know what I mean. Ground rules, so an example of a ground rule is if I'm going to modularize MEP and put big modules in, it can't then interfere with the next trade, which might be the dry lining, that it then can't fit them. So they all have to relate to each other and not interfere or influence each other in a bad way. Creating a common understanding, which is amongst the team. How do you create that? Understanding the engineering principles of the product family, and again, how these things are transported. What's the maximum transport envelope? Do you split things to then pre-assemble together on site? Design guidance. So if you haven't got a contractor on board and you've engaged with design organizations, you want them to design with DfMA in mind. So that's a set of guidance. And then understanding DfMA benefits criteria. And I'll come on to this right at the end because there is a cost of within MEP DfMA because you put relatively low value things in frames, and that frame has a cost, and you're transporting, in some cases, a big volume of something, a group of modules with low value stuff inside it. And I'll touch on that a bit later. And then there's the other criteria, you know, what are the time benefits of this and how do you maximize that? Quality benefits, maintainability benefits, etc. So a review of MEP component set. So it's about understanding the MEP design, and MEP systems pass through buildings from the large end to the small end, the large end being the prime movers, the plant rooms, and the small end being the point of use, and it could be a sink, electrical socket, an air conditioning unit. And then identifying those into systems and grouping them in such a way, deconstructing that design, and then reconstructing it with the product family. So that starts with energy centers and plant rooms, volumetric space, plant equipment modules. So these might fit within a building plant room into onto a concrete slab, on a roof, etc. But within a larger structure where they don't have their own structure. Vertical distribution modules, also known as risers, horizontal distribution, terminal distribution, which in this case is fan coils, modular wiring systems, bus bars, volumetric spaces, which can be IT hubs, whole operating theatres, classrooms, bathroom pods, and kits and parts. Kits and parts are everything that connects modules together and modules to other things, which could be field-mounted tanks, underground piping, etc. So these are just samples of composite plant rooms. So that's the one on the left is too big to get on a lorry itself, so it's split. So all of your field joints are along the joint line. And that's what it looks like when it's installed. Composite plant rooms. So just to focus on this, you can see a lot of framework and you can see floors. So these floors, for instance, add value for the purposes of mounting that equipment and transporting it to site and placing it in position. When it's installed, it doesn't add value because you've got a floor on floor. And I'll come back to that shortly. So vertical distribution risers, so they're built in line and you build so many together and then dispatch however many you need for consumption on site. And then the last one remains to be connected to the next one. And these all have large, in this particular case, location pins. So when they come back together on site, then all of these services align perfectly, and it's just a matter of clamping them together. And as you can see, they've got riser floors as well. And this is a picture of horizontal distribution modules in manufacturing. And as you can see, these, and these are risers as well. So these are all built with everyone working at waist height and materials delivered to the point of use. And then terminal distribution modules. So these are fan coil modules in a frame with ducting, piping, BMS controls, etc., etc. And they're just lifted into position and bolted invariably into unistructure and cast into the slab. And these were underfloor data center modules where they were pre-wired, and there was an A and B supply, all pre-wired, and then the A loom comes back and the B loom comes back onto the opposite module. I think these were 12 meters each, and then they're installed on site, and then the loom A goes to B and B goes to A, and it's complete, just needs to be connected to the distribution units, the power distribution units. And then interconnecting kits of parts, because you get great value from installing modules quickly, but then you want to connect them up quickly, so you build whole plant rooms in much less time. But again, you'll see these modules are characterized by lots of steel. So Nostafs, touched on that, 100 million MEP, all of these facilities started in 2006, finished in 2013. Quite a long project because it was delicately built on a live hospital site. So the main features implemented, the production system, synchronized workflow, and to synchronize the site element or the in-field element has to pass right through the value chain, through manufacturing, through procurement, into detailed design, back into design. So you're getting the right drawings at the right pace to suit the takt time of the project. Planning and production control using Last Planner, digital engineering, ABC analysis, DfMA, takt planning, mobile work cells. Just to touch on that, we worked together with groups of pipe fitters, duct fitters, partition guys, electricians, and designed particularized work cells for their phase of the project. So when you're in a big open space, the characteristics of the equipment changes to when you're going in and out of a completed room, second fixing, putting lights in and, grills, etc., and creating a common understanding. So that's not there to read all of that, but this is one of 63 construction zones, and these are the corridor modules. And you can see that there's lots of other services going through the space. So we deliberately distributed ducting through the spaces because it's A to B stuff, doesn't necessarily need maintenance, fire dampers do, etc. But you can see from this, there's thousands of components. So there's 18 modules and thousands of other components to coordinate if you want to create a workflow. So that's just a snapshot inside the model. And every component was a specific object. So when we looked at the amount of corridor modules, it was about 1,200, and we thought we're going to standardize on these. So we had, in agreement with the architect, 2 corridor widths, hospital street and a normal corridor, and 2 ceiling depths. So sometimes you have a 2.7 meter ceiling, sometimes you have a 3 meter ceiling in operating theatres, for instance. 4.2 slab to slab. So that gave us 4 types of framework that then supported the services within it. So in the hospital streets, we put everything that was maintainable, all the electrical functions, electrical services, wet services, medical gases, etc. So that was a high cost of framing all of that relatively low value contents. So we developed an ATIF, assembly, transportation and installation frame, which is used for assembling, transporting and installing, and then reused. So this is a short video clip, hopefully it works. So these are 6 meter long modules. So the module frame was the 80 frame was 4.8 meters. So you had a 600 overhang. Connecting to the next 600 overhang gave you a 1200 centers of the brackets, which are these, which is the design. We put a matrix of cable tray in there. We weren't interested in reducing it down as cables peeled off, because that's a penny. So we just standardized on that, just put a matrix everywhere. And then this is what I call mass customization. The piping was configured to the room it serves. So that was all built as spools from the model and then assembled to that particular module that located in the particular space on each floor. So 5 were built together, 4 went to site, 1 remained. So we get connectivity. And then the next 4 or 5 are built up to them. So they come to site with precast modules in tram lines, as you can see, which cross over with the unistruct frames, bolted into those, and the frame drops away. So we had 40 of these ATIFs and 1,200 modules. So we really drove the cost out. And those frames can be considered an asset for your next project. And they're reconfigurable because there's spaces in the middle to change the widths to suit the different corridor widths, and inserts for the different heights. So they're mobile jigs in essence. So these are the modules in our facility. So line side, we had the 40-foot frames, and obviously as the different modules were configured, then the frames were changed as they came back from site, either narrower or shallower, or one or the other, and then reused. So there's that note about the 1,200 modules and 40 ATIFs. So the first trade here was fitting the cast iron drainage, and then the modules were fitted, and then ducting was fitted afterwards because some of that threaded through the modules. So we wanted those modules in place first. So that's with the module deployed. And from a tolerance point of view, these were cast-in inserts, and these were not that accurate, and we expected that. These are precast slabs. So that didn't matter because the tops of these were slotted, so we could pick up, if this ran this way, we could still pick it up here. So we compensated for the difference in tolerances between MEP and structure. And then everything else, parts kitted, so all the subframes were, sorry, the sub-supports were pre-assembled, and they were standardized. So you either had containment area or you didn't, electrical basket or you didn't, as such as that, or you just had piping below, or you had both. So we just had hundreds of these made and delivered on carts to the point of use. And then all the other consumables were on these trolleys that we designed with large center wheels and casters at the end so they could rotate on the center axis. And they were topped up. It wasn't a perfect Kanban system, but our logistics team just topped up when the bins were empty or getting towards empty. So they never ran out of nuts and bolts. We weren't too worried about theft, which is fairly prolific in some areas because it's low value. Where we had copper piping, where we're field running branch piping that weren't on modules, then we had secure modules. Sorry, secure trolleys. Yes, same thing with cast iron fitting. So these came from the suppliers and they stacked on top of each other when they went back. Large wheels to maneuver. Very useful trolleys and heavy duty because cast iron piping is quite heavy. And then ductwork is the same. So you can see this waiting for loading in the ductwork yard. And then delivered straight to the point of use and then put into position. So just to touch on that, our duct fitters would normally allow 18 meters per day per pair. That is an operative and a mate, as we call them. We got them up to 40, not just by this, but facilitating their productive workflow, that they had their own space for 1 week, all the information provided, all the prerequisites, 7 construction flows. just leaving them to work through that. So they're just assembling ductwork. And it's an interesting point on whether you should put ductwork on modules, but large ductwork is a module in its own right, and it really doesn't add value. So you don't necessarily have to do it unless it can be incorporated with other services. So we also design these large platforms. So these are on wheels with a walk-up access and then a large linear working platform, because these are the modules here, the ATIFs, and these are the branch lines that come off that. And ordinarily, these guys will go up and down in a MUP, but traveling vertically and horizontally in a lean system is a waste because you're traveling up and sideways and up. So installing linear systems needs linear working. So these don't cost much. These are about £50 a week to hire, and they're much more productive. You can't see it on here, but we put Kanban bins, parts bins on these, and then again, their parts were replenished at the point of use. So they don't have to come down and go and get bits and then walk back up, etc. And mobile information centers, so drawings. And we might say, well, we don't use drawings anymore. Everything's on an iPad, but we do use drawings, and they're still stuck to walls unless you provide equipment for them not to be stuck to walls. So the outcomes, just checking time, sorry. Commissioning period not compressed. We had on-time delivery of each phase. The P21 was a different commercial arrangement with the client, and the client got gain share. So we shared the profit that we made, or the lower cost. 44% was made off-site. We had almost 40% less on-site labour. Less workers were exposed to lower risk for a shorter period of time. Good ergonomics, improved quality of work, and there's a whole question about de-skilling as well in assembly, but that's a whole other topic, because skilled operatives don't necessarily like to be de-skilled by assembly, so that's a good learning point. And then productivity gains by eliminating process waste. So overall, we saved 8% on our labour budget for this job, which contributed to the margin at the end of the job. And when we tested all of the other peer projects in the business, all of which were large healthcare projects, not doing this, then there was a lot of cost blowouts on labour. All other things being equal, you really need to control the labour. So Northern Water Treatment, a complex water treatment plant. I knew nothing about water treatment, but spent a lot of time at its sister plant, watching that being built in a traditional way, then understanding how not to do that. So I won't explain all the technology, but it's basically a brine desalination plant as part of the coal seam gas.
Hi, Peter, it's Margie. I'm just going to give you a little time check. We have about 15 more minutes. So just want to give you as promised.
Okay. So the value to the customer was to get the water treatment in place to produce gas. You can't produce gas without treating water. We were fly in, fly out, rostered work periods, and there was absolutely loads of oil and gas projects going on across Australia. So there was an extreme skilled labour shortage, difficult working conditions, and also, I haven't put it here, but heavily unionised. And unions don't necessarily like you to take labour off site for the obvious reasons. So what did we do? We self-delivered a bin model, comprehensive DfMA solution divided into 5 plant locations, 32 module groups, 262 modules, and kits of parts. Kits of parts in this model are all the pieces that come off a module. This is the GE process equipment, pumps. Parts kitting strategy, and we implemented last panel, production control. I'll have to speed through these, but this was the site in Wandoan in Brisbane. Assembly facility we set up in New South Wales that manufactured the steel and had it galvanized, and we brought all the contents into a lay-down yard, assembled the modules with GE kit that came back from site. This was implemented after the start of the job. So we were some way down the design funnel. And then modules and kits and parts went back to site. So we had 3 crews offloading and assembling modules. So from a union perspective, riggers did that. They could only do that. Mechanical and electrical then connected the mechanical and electrical components together. And then 1 crew fitting mechanical interconnecting parts and GE kit. So large range of modules. These are our assembly facility. So these are the brine concentrator towers made on the side because they're quite tall. Pumping stations in the large ponds we had to build. So full range of equipment. This is just some simple snapshots, but these are Rubbermaid industrial trolleys, so you can buy them. And garage mechanical stools. So these guys don't break the back bending down all day. They just scoot along and put all their bits and pieces in there. And we customized some 20-foot containers. So as opposed to going to a store somewhere in the laydown yard, asking for your nuts and bolts and then putting them in a van and bringing them back, or a ute, sorry. We delivered all the kits and parts at point of use. So we had about 20 of these. And gaskets were on a gasket wall, bolts were in a bolt rack. And because some of these bolts were pre-galv and are quite large, galv to manufacture, we would run them up here, test them all, and then put them on a trolley and then off to the point of use. So the path of construction was through the plant complexity, most complex first. We built a crew balanced production system to work at an even takt time through the roster period. So the bases were poured ahead of modules, module assembly in sequence, process kit in sequence, kit of parts, and then the next module group commenced. And just to touch on how we did. So up to 85% of large bore piping, some of it was 5-foot diameter, down to micro bore instrumentation piping. The SUF tanks, 90% off-site, clarified tanks 86, 70% less labor for the module groups, which is mechanical electrical labor, 60% less guys assembling SUF tanks, and 60 for clarifiers. And we saved 37% of the cycle time to get to mechanical completion and 20% of cost compared to the sister project. So next generation DfMA. So again, these are just models of modules. You'll see these are characterized by framework, inertia bases, concrete, etc., just to transport these things to site. Do they add value when they're installed? Some of it does. So the modules we've designed now look like this. So you need an upright to support the headers, but steel piping is much stronger than the steel frame. So make that an integral part of your module. Obviously secure it in such a way that it acts like that. And then when it's on site, you release it if you need it for thermal movement. And a lifting beam, also make it part of the structure, but then it adds value because you then get your motors out. No inertia bases. So the floor is the base for all of them, which is cheaper than 3 inertia bases with concrete. And you put the whole set on 4 AVs, not individually. So the frame is everything that just adds value. So it acts as a ATIF, and it doesn't add further cost that you would add to your value that you sell to the customer. The customer shouldn't really pay for that. So there shouldn't be a cost for DfMA, an additional cost for DfMA. So engineers design model. This is a large distribution corridor on a large horizontal plant room. So this was after DfMA development. So with an inbuilt floor. Why do that? Because it separates workflows as opposed to stick building progressively along here and blocking access. You can get to your joints for bolting up. You can pull your cables. You've then got it for access and maintainability in the future. And if the customer wants to then reconfigure, change cables, add things, then you've got accessibility. So at a very small cost, you're adding a lot of value from a DfMA perspective. And then services distribution, some very clever, agile bracketry. So this is a pre-manufactured and it's seismically rated as well. That's infinitely variable. It's like a Meccano set for those people who are old enough to know Meccano, which unfortunately I am. That it's just configurable in any way. And especially in hospitals, if you're waiting on technology selection and you don't know what you're going to fit in a certain space for a CAT scanner or whatever, then put these in and then coordinate a space with these in. So it's reconfigurable, easily reconfigurable, and very easy to install. Benefits assessment. So there are benefits from a safety point of view, from a health point of view, where you haven't got people on site bending, twisting, lifting, carrying, so their long-term health improves. Difficult to measure. Quality is improved. Time, my experience says that on paper you can save time. DfMA gives you an insurance policy against not overrunning, but I've also seen it the other way. So what do you use that additional, that betterment for? Probably to not compress commissioning, but it depends where DfMA is on the critical path. So if it's not on the critical path, it might not give you an overall time benefit, but it might defend commissioning periods. It depends on the project. Reliability of equipment should be the same, but I think if you, it's in a better conditions when it's installed. If you've got built-in accessibility, you've got built-in accessibility, and it's part more of the BIM process to make sure that everything's reachable and maintainable, etc. And I think that's it. Yes, as it says there, I could go on forever, but Margie will cut me off.
Pete,
so I hope you got that.
Pete, that was fabulous. Hey, we've got a question here from Zig Rubel. So I'm going to unmute him and let him ask you that in real time.
Okay.
Zig, are you there?
Yeah, can you hear me?
I can, Zig, yes.
Yes.
Okay, great. Great presentation.
Thank you.
So my question, so we've had some other thinkers like yourself talk about industrialized construction. And my question is DfMA a evolution to industrialized construction, or will industrialized construction just fall under DfMA? And tangentially, if you want to go there, how would your journey on the mountain change with industrialized construction taken into account?
So that's a very good set of questions. The only way I can answer that, I guess, is by experience. So when you go back to Worcester Hospital, that was a version of industrialized construction, because we balanced takt time. We had 2 weeks takt time for a larger construction zone, but nevertheless, it was balanced. But there was no pre-assembly. We didn't modularize. I didn't really understand about modularization. This was in 2000, something like that. I didn't learn about DfMA until I went to Crown House, who had their own facility. So we industrialized just on parts. What we did recognize is those parts were either prefabricated or made to order, let's say, or made to stock. So we synchronized that through the logistics team to point of use. So DfMA, I can't remember the exact question you asked, but DfMA isn't industrialization. DfMA is an evolution from industrialization, because you can build without having a facility. So if you're remote, you might say it's just too expensive. So I could pre-assemble on site, for instance, but offline. So I think industrialization and becoming leaner and safer and more ergonomic, you can do without DfMA. DfMA really does benefit you, because even if you're industrializing parts, the parts assembly process, You still need quite a lot of people to do that, depending on the complexity. With modules, you can do 8 weeks work in 4 days, you know, in a complex corridor, hospital corridor installation. And those modules are built off-site by operatives in a much safer and productive environment. So Zig, I don't know if that answers your question, but because you can separate them, you can industrialize without DfMA. But that, if you think how cars are built, an engine is a module, isn't it? So they don't deliver all of the parts of an engine and assemble it for about half a day under the hood of a car, do they? It just goes in. But the whole process is industrialized. So the idea of the ATIF that I described earlier is, the concept of that is the engine comes in on a conveyor, it's dropped into the exact position in the car, and then the conveyor goes off and goes and gets another engine. That frame doesn't stop with the engine. So it's the same with an ATIF. It deploys the module, then goes back via the road and gets another set of modules. So it's a betterment of industrialization. Does that answer your question, Luke?
Yeah, it did. Thank you so much.
Great. Pete, we have a question here from Paul Beckman. Paul, I'm going to unmute you and you can ask your question.
Hi, Paul.
Yeah, Peter, my question, the image that you showed where they were assembling the overhead modules off the large scaffolding, I believe you said that that was like in a hospital corridor type environment, but there's no wall framing. And I'm wondering how you deal with the wall framing after all the MEP goes up unobstructed like that.
So what we did, Paul, so that scaffold was the branch lines coming off the ATIFs. We only put the ATIFs modules in the corridor. So what we agreed, so that the frame on the ATIF is an inverted Christmas tree. So it's bigger at the top, smaller at the bottom. And so we agreed with the partitioning company, the dry liner, that he would place his head tracks. You may have seen that on one of the pictures. So he placed the head tracks as a prerequisite. As part of the TACT plan, the balance plan, he spent a week doing a construction zone, which is 1,000 square meters approximately, putting all his head tracks. So all the rooms were there, excuse me, without actually being there. But we designed the ATIF to then give him clearance to then put the dry lining up. So there was sufficient space for him to do that. And that space was then accessibility for us to populate the cable trays with cables, to then connect the modules with piping, etc. And sorry, we did that before the dry lining went in, but especially for accessibility for maintenance. So you've always got that gap between the sloping side of the services to the wall, the wall to be fitted and sealed, and then that space is then accessibility to get back to the equipment for maintenance or replacement. So if you remember, one of those ground rules was not to disrupt the next process, because we could have put all of the dry lining in and formed all of the stud and first side, as we call it, and then put modules in, but it's extremely difficult. And because of the value of MEP labor, or the volume of it as well, it was a high cost premium versus the partitioning guy going in afterwards and cutting around services. So it was done in conjunction with him. We designed the workflow together. What I haven't shown here also, Paul, is the equipment we implemented for the dry lining handling, which was some really good ergonomic equipment that's available. So the stacks of dry lining were all at waist height on carts that deployed these and tilted up, went through a door and tilted back down. So really clever stuff. So this isn't just MEP. We looked at the whole fit out process, but I've focused on MEP.
Okay.
Because that's.
Thank you.
Sorry, I'm going on, Paul. Sorry, I'm rattling on.
No, you're fine. Thank you.
Yeah, thanks for that question, Paul. We've got time for one more question, and I'm going to unmute Danielle Adams. Danielle, if you're still here, do you want to ask your question?
Hi, yeah, can you hear me?
Yes.
I can, Danielle, yes. How do you do?
Good. So One question, because this is one that I'm getting a lot on a current project, is when you're connecting from a header down to equipment, like how would we utilize DfMA for that? And I think it plays into the kit of parts strategies that you were mentioning, but especially when you don't have identical systems, is it still successful to implement some kind of kit of parts strategy?
100%, Daniel. On the Northern Water Treatment Project, we had 1500 diameter, can't remember the name of it, fiberglass ducting piping. Sorry, there's a better name for it, but it's gone. And so we had field joints. So green ends, sorry, a green end is a 150 over length. And then when you've got, say, a fixed piece of equipment on site, like a field mounted tank and a module group, you would have most of it prefabricated as a spool with a green end, which is an over length. And then you'd measure that gap when you've fitted the piping, or depending where the tank is, and then just cut that field joint, cut that green end so it fits exactly. Or you measure between the two, depending where your fab shop is, and then get that made as a spool piece to make that final connection. That's the only way you can deal with tolerancing, either field green ends for field joints in a kit of parts, or site measurements for the difference in tolerances. Because some of these things might not be there, you know, whatever you're connecting to might not be there when you fitted your module group. Does that answer your question, Danielle?
Yeah, I think that helps. Thank you.
Okay.
Peter, this was so fantastic. We can't thank you enough. You hopefully are going to go out for a well-deserved beer now, as the rest of us start our days, or maybe go to lunch, wherever you might.
I'll be thinking of you.
Thank you so much for your time. It was really a terrific presentation.
Okay, thanks.
For all of you in the audience, this concludes CIDCI's online salon. This session will be recorded and placed on the CIDCI website as soon as possible. To join us for future webinars, be sure to subscribe to our newsletter on our website, cidci.org. Our next salon is next Friday, August 6th. It's going to feature AIA fellow Lance Hosey discussing what happens when buildings design themselves. He's going to be in conversation with CIDCI board member and NYU professor, Samiha Aragon, and your host will be CIDCI board member, Zig Rubel. Today, we also bid farewell to Monica's Whistler and welcome Katie Olson as a magic maker behind the scenes who makes all of these events possible. We're so grateful to both of you. Thank you for joining us. And as always, if you have thoughts or comments, please reach us via the CIDCI website, contact us link. Thank you and be safe.